we are now going to have a look at how to integrate by parts, okay? To integrate by parts here. Integration by parts, I actually think, is easier than substitution. Substitution, I didn't want to say this at the time, substitution I think is the hardest part of integration. But I didn't want to say that to you because then you would have thought like, oh my God, it's going to be so difficult, we won't be able to do this. Integration by parts looks like it's the most complicated, but actually it's one of the easiest ones that just follows like a set rule of things that you need to do. Substitution, there's kind of not so many rules. You have to be able to figure out all the different things that are going on. So I've said here, we're going to try and integrate x cos x with respect to x, and I've just put question mark, question mark, question mark, because we don't know how to do this yet. X is not the derivative of cos x, so we've got kind of stuck about how we might be able to integrate it. And I've said, just as the product rule we use to differentiate the product of two expressions, we can often use, important word here, often, because we shouldn't always use it, we can often use integration by parts to integrate a product. I've already said before, sometimes to integrate a product, we would do the reverse chain rule. Sometimes to integrate a product, we would be able to do substitution. And sometimes we will use integration by parts. And the more practice we do on this, the more familiar you'll become with when you should do this. Now, the formula for integration by parts says u dv dx. You take, this is the thing we're trying to integrate. You're going to integrate this with respect to x. And what it will be equal to is u times v minus the integral of v times the derivative of u with respect to x dx. It looks really complicated. I'm going to just rewrite this formula in a way that might be a little bit easier. So instead of doing it as u dv dx, I'm going to say u v dash, and that just equals u v minus v u dash dx. We've kind of been familiar with some of those things that we have. Now, what this means is you get given this thing here. So the two things that you have that you're going to select at the beginning are no longer u and v like they were in the product rule. In integration by parts, one of these two things will be u and the other one will be v dash. If you know what v dash is, you can work out what v is. How would you work out what v is? By integrating, because remember, to go from v to v dash is differentiating, so to go from v dash to v is going to be integrating. So this is the weird thing. You start off with two separate things, apart from instead of it being u and v, it's u and v dash. You then, on the right-hand side, get a mixture of u and v, so the integrated part of v, and then the integrated part of v multiplied by the differentiated part of u. And you're probably thinking, where did this formula actually come from? So before we even do an example with this, I'm just going to show you where this formula has come from to give us a, just so it's not made up, okay? Now, it comes from the product rule. And the product rule says that if you wanted to differentiate with respect to x, u, v, you would have u times by dv dx plus v times du dx. Our version of that usually is we sometimes say that uv differentiated is uv dash plus v u dash. Okay, I'm just using these notation here so that we can try and make it look like the formula that we have up in the orange box here. Now, the thing that sort of looks like the subject is the u dv dx dx, the u dv dx. So I'm actually going to keep this bit as the subject, and I'm going to rearrange it so that that goes onto the other side. So we have the derivative of uv minus v du dx is equal to u dv dx. It's almost looking like this thing that we've got up here. I'm actually going to just do an extra step, and I'm just going to swap everything around. So I'm going to write this over here. So that's u dv dx equals the derivative of uv minus v du dx. Now, the only thing that needs to change to go from this line to this orange line, can anybody spot what needs to change to go from this line to this line? Yeah, multiply by dx and integrate. So in other words, we're going to integrate this with respect to x, this with respect to x, and this with respect to x. Now, if I integrate this first bit with respect to x, you get u dv dx. I'm going to just leave this bit for a second. Then I'm going to integrate over here v du dx. Whoops, I missed off that I'm going to do that with respect to x. If you've differentiated uv with respect to x, and you got this, when you integrate it with respect to x, you would get uv. Okay? I should have probably said at the beginning, this proof is not something that you'll be expected to replicate, but I like to show you where it's come from, so it's not just some random rule that's been given to you. Okay? It's something that, it's something that comes from the product rule. It's like a variation of the product rule. And the best way of understanding this is by doing some practice with it. You know, I'm doing my evening study course. I was doing some work last week and this week, and I have to use the product, not the product rule, integration by parts, like non-stop. So it's something that just comes up as like just a regular thing that you'll need when you do maths, like at university and things. Okay. So let's dive in and actually see how this works. I've written something at the top here that I've stolen from some of the stuff that I was looking at uni, and the difficult thing that you have to do at the beginning is to decide which of these things is going to be the u and which one is going to be the v dash. And often the way that you choose this is if you have a logarithmic function. So if you have like an ln, you would make that become the u. If you had an inverse trig function like arc cos or arc sine, you won't have to do these unless you're doing further maths. You would then choose that to be u. If you have an algebraic function, then you would choose that to be u, then the trig function, and then an exponential function. So which of these two, using that Lie8 list, should be the one that we pick as u? X, because x is the algebraic function. Okay? So I'm just going to do a quick reminder that our formula says to integrate by parts, it's u v dash with respect to x is uv minus the integral of v u dash, I'm not going to do a mixture of things, dx. And the things that we're going to pick here is x is going to be our u, and v dash is going to be our cos x. They always will be u, v dash, and I deliberately write them in this way, because do you remember when we did the product rule, we did u, u dash, v, v dash. So we're going to do them in that same way of like filling in the gaps. You go down to differentiate, you differentiate to go down, and you integrate to go up. Now, when I differentiate u, I get 1. And this is why we choose x to be u. Because when you differentiate x, you get something that is simpler to deal with, which means that you're going to have something simpler to integrate in this second part of the formula that we have here. That's why we choose x as the u function. Now, what would v be? Sin x, because sine differentiates to cos, so we get sin x. So we have already used this one. This one has already come up in the question, so we won't be using that pairing of them again. What this therefore is equal to, we get told in the question that it is uv. So uv are these two things being multiplied together here, which will just be x sine x. Then the next thing we're going to do is we're going to take away the integral of v u dash. Now v u dash is these two that we have here. Do you see how we previously used the blue pairing? You're now going to use the red pairing. You're always going to have the bits that are integrated at the diagonals. And this is a really nice visual way of actually remembering the formula. I don't remember the formula. I remember the pattern that I do when I do this thing here. I actually wouldn't usually write out the formula. I would just write this out and I go, well, I know it's the top two for the beginning bit, and then it's minus those two bits for the next integration. So when we have the next part that we have here, we're going to subtract the integral of just 1 times sine x, which is just sine x dx. This thing that we have here, we probably want to put that somewhere else on your page, otherwise it can get really confusing. So if we finish this, we get x sine x minus the integral of sine x is minus cos x, so it'll be minus cos x plus c, which is x sine x plus cos x plus c. Because you're subtracting the integral of sine x. And the integral of sine x is cos x.
Plus c.
Yeah. Which bit are you confused with?
When you integrate sine x, you get the minus cos x plus c together, right?
Oh, so no, at the very end, you just add in the plus c at the last minute.
Okay.
So we could have added the plus c when we did this bit of integration, but we only need one constant of integration for the entire thing. So when you've done your last piece of integration, you add in the plus c. You don't need to worry about whether that's positive or negative or anything. I see what you're saying now. So let me just give you a chance to write this down. Then we're going to differentiate it to check that it gives us the right answer, okay? Look how much easier it is than substitution. No, because if you think what would happen if you did these the other way around, if you had the x here, what would you get here? You get x squared over 2 or half x squared, which means you would have a half x squared and then some other trig function that you'd have over here. So your function is going to get more and more complicated if you do integration by parts the wrong way around. Okay? No, because it will just continually get more complicated. Ruhan asked a good question. He said, what would happen if I picked these the wrong way around? If I didn't pick u as x, maybe I picked u as cos x instead. Well then, if you did that, you would have had, if u was cos x and v dash was x, u dash would be minus sine x, because cos differentiates to minus sine, but v would be a half x squared. And if I was going to integrate this, so I'm trying to integrate x cos x, look, x cos x is from those ones, that would be equal to these two, which is a half x squared cos x, minus the integral of these two multiplied, which is minus a half x squared sine x dx. This thing here, what do you notice about this thing here? Does this look nice to integrate? No, it looks even worse to integrate than what we had to start with. So the point of integration by parts is to try and make this second thing that we're integrating here more simple. That's the plan of what we're always trying to do in these questions. We're always trying to reduce the complexity of this starting thing into something else. So this is why we wouldn't pick it that way around, because it makes things more complicated. Let's just actually check. It's quite nice to see if we differentiate this to see that it actually works. So let's just let's say let y equals x sine x plus cos x plus c. Let's differentiate it to see what we get. See if we can do x sine x differentiated using the product rule. Let's try and do it without writing down u and v. Let's differentiate this and keep this the same. So you get sine x. Let's keep this the same, but differentiate this. Let's differentiate this. Minus sine x plus c differentiates to 0. So dy by dx is equal to x cos x, which is what we wanted it to be because we were trying to integrate x cos x. So it's really nice. It's kind of cool, actually, that you wouldn't expect something that looks like this to differentiate to this, but it does. So this is just our check to see it works. You don't have to check to see it works. It's because this is our first example. I wanted to show you that. We're going to try another example. So this time, we are going to be having a look at doing x squared ln x dx.
Use ln x.
Good. U is ln x. Do you remember on your memory page that I gave for you, for integration by parts, I said on that memory page, for integration by parts, ln takes priority for u. So we have an ln x here. So this is the thing that is going to take priority as u, and this is the thing that is going to be v dash. You can also see in our list that we've got here, our Li8 list, logarithmic function is the thing that comes first. So as soon as you have a logarithmic function, like an ln function, that takes priority for what you will assign to be u. Now, start off by doing this pattern that I've said before. You have u equals, you have v dash equals. That means that u is ln x and v dash is x squared. So v is the integral of this, which is a third x cubed, and u dash is 1 over x, okay? Why do you think we've put ln x as the u rather than as the v dash?
Because the 1 over x will cancel out.
Because the 1 over x is going to do some cancelling out when we use it. And how can you integrate ln x? We're going to learn how to do that later, but it's messy. You have to use integration by parts. Right now we can't, okay? And I wouldn't even want to if we could, because it's very, very messy. So, yeah?
For ln x, is it like you split it, like 1 and ln x,
Yeah,
and then you do that?
yeah,
Okay.
you do. So with this pattern we've got here, the visual way that I want you to remember this is, okay, cool, well I've already used the uv dash because that came up in the question. That's the thing that I've used up here. So the integral of x squared ln x dx is going to be equal to uv, so these two things together first of all. Maybe I should have done those in a different colour actually, so it doesn't look like I'm writing the same stuff. We've already used this one, and we're then going to be using this one. So the integral of x squared ln x dx is equal to uv, which is a third x cubed ln x. And then we're going to minus. Don't forget that it's minus. It's not like the product rule where it's a plus. You're going to then minus the integral of the other two things that we haven't yet integrated, which are these two things here, the pair that we have on the other side, which is 1 over x times by a third x cubed dx. So we get a third x cubed ln x minus the integral. Let's just think about what this should simplify to. A third x squared dx. So we're nearly there. A third x cubed ln x minus the integral of this. So we're going to raise the power and divide by the new power. So you get a 9th x cubed plus c. And that's our answer for that. It's not actually that much working. People often think integration by parts is going to be really, really heavy with the amount of working that needs to be done. Should we check to see that it works by differentiating it? Just for fun.
For fun.
Yeah, for fun. Okay, so we've got y equals a third x cubed ln x minus a 9th x cubed. Okay, I'm going to do this product rule, but I'm actually going to do the product rule properly. So I've got a third x cubed, and I've got ln x. U dash would be, what's the third x cubed differentiated? X squared and 1 over x. But it's nice to see that it's correct, isn't it? So we get that dy by dx is equal to u v dash, so that's a third x cubed times 1 over x plus these two, plus x squared ln x. And then this thing here is minus a third x squared. This bit here simplifies to a third x squared plus x squared ln x minus a third x squared. So it does differentiate back to x squared ln x, okay? This is just checking or showing it works. You don't need to do this. It does work. It does give us the right answer of x squared ln x. Which bit?
It's like showing instead of capital N.
Showing. There we go. Okay. So I'm going to ask you to do exercise 11F, question 1 and question 2. But before we do that, I just wanted to say that there are a few things that I'm not expecting you to memorize just because they're kind of tricky. These are some functions that you're going to need to know how to integrate. They are in the formula book, but I think these are quite rare for them to come up. We're not going to prove these, although I think we've actually looked at some of these things in the past, that when you differentiate ln sec x, you get tan x when you differentiate this. But you might need some of these expressions in the questions that I'm just about to ask you to do. So it's exercise 1F, question 1 and question 2, but not part D in question 2 for me, please. Okay?